Hi everyone, my name is Isaac Berry from Berry Science Lab, and today we're going to be looking at a nice problem involving the Coriolis effect. So the Coriolis effect is kind of like the centrifugal force, in which it's a kind of pseudo force that appears to be affecting objects when you're viewing them from a non-rotated frame or a non-rotating frame. So let's say we have a rotating disk, and you have this view that's rotating with the disk, and then you have this view which is just looking from the side. It's not rotating with the disk at all. In this view, maybe a ball will fall this way with respect to the disk, but on this view, this same ball would appear to be moving this way due to the Coriolis effect and centrifugal force. So the Coriolis force in specific looks something like this. So let's say we have the Earth, right? No. It's not satisfying. Okay, good enough. So now this is the center of the Earth. This is Null Island. And now, let's say a man is standing right here at this point on the Earth. And let's say he has co-latitude, so the angle formed right here, where this is the North Pole, and this is the core of the Earth. This angle right over here, let's say it's theta. So this is the co-latitude. And it's called that because it's actually just the it's the complement, I forgot, to the latitude. So it's the co-latitude complement to latitude. Okay, great. So now that we have that out the way, he fires. Oh my goodness, dude. What is this? He fires a gun directly due north. Now that's not going to look up like it does in 2D situations. The North Pole is this way, which means that by firing the gun due north, he's going to be firing it like this, tangent to this arc. Now, if we want a 2D depiction, maybe it would look, something like, I kind of just want a quarter circle actually. Maybe it would look something like, no, theta's too, what? So then due north is going to be tangent to the circle this way, right? Given that this is the North Pole. All right. So now, if the bullet has mass m, initial velocity v naught, and the Earth is turning with angular velocity omega, then we want to find, and yes, I know that the symbol is lowercase omega, but the textbook that I'm taking this problem from which is problem 9.9, I believe, of, no, it's not Stewart. It's John Taylor's Classical Mechanics. So problem 9.9 of John Taylor's Classical Mechanics, check that problem out if you want to see their solution. But right here, we just use this handy formula, and you might ask, well, what's the angular velocity vector? Well, you use the right-hand rule. If something's curling around this way, then the angular velocity vector will be traveling up. So you take your hand, your fingers are curling this way, and your thumb points up. On the other hand, if it's curling this way instead, your thumb is going to be pointing down. So curling, let me see, that's counterclockwise. It's going to be, is that counter? Yeah, this is counterclockwise. It's going to be this way. And then curling clockwise is going to be this way. So in this case, we're just assuming that that's clockwise. So let's assume that it goes clockwise. And so, but it's going to make things a little bit more difficult. So let's assume it's counterclockwise instead. So that makes the angular velocity vector up, always. Now, if we want to calculate the magnitude of the Coriolis force, that's just going to be minus 2m, the magnitude of the cross product. So, everything seems to be found pretty easily by just plugging in, except the angle between omega and v. What's that going to be? Well, omega is pointing up this way. This is the angular velocity vector. So, what does that mean? Well, we can't do that, sorry. So, since this is a tangent right over here, it allows us to draw this nice little right angle. And so, what does that tell us in this situation? Well, if we kind of extend this out to a very long line, then we're able to tell what angle it comes from with respect to the horizontal. So this angle right here is just the latitude, equal to the latitude, 90 minus theta, right? So what does that tell us about this angle? Well, this is a right angle, so this has to be equal to 90 minus theta, which is just equal to theta, which makes this angle just equal to the latitude 90 minus theta. Okay, simple enough. Which means that it just minus 2m omega v naught sine 90 minus theta, or rewritten more simply, minus 2m omega v naught cosine theta.